Let's continue talking about liquids that are boiling, or what happens when liquids are boiling. We already know that can occur at different temperatures depending on pressure. And we also discussed that, for example, water, and this is true for other liquids as well, that some of the water molecules are evaporating even when we are not at the boiling point. So there is a little bit of vapor pressure always present above the surface of the liquid. And I told you that at a given temperature, if it's kept constant, that we have the faster molecules that are evaporating, and then those molecules also can slow down and then condense. And so we have the rate of evaporation and the rate of condensation that's supposed to be equal, I said, but of course that's not entirely true, because you probably have a good feeling that if I have a cup of water and I leave it out in the sun, and that's going to completely evaporate even if we don't ever reach 100 degrees Celsius. And that's of course because the molecules can spread out. So in a way, if we don't have a sealed container, the rate of evaporation is going to be larger than the rate of condensation. But in principle, that concept makes sense. And so when we have a sealed container, we can reach this so-called equilibrium. We call that a dynamic equilibrium because it's constantly evaporating and condensing. And this is just to show that initially, when you start the process, let's say you are at 25 degrees, you have the rate of evaporation here that is constant, and so initially you're going to have evaporating that increases. The rate will increase until it matches that of the rate of evaporation, as long as we keep the temperature constant. Alright, so we are looking at a partial heating curve here. We are plotting a liquid, in this case it's water, that is being, first of all, heated from room temperature to the boiling point. And so that goes back to the thermochemistry chapter number 9, I believe, in this particular book, where we used the value for how much energy is required to warm up 1 gram by 1 degree of water, which happened to be 4.18 joules per gram per degree. And so that we can calculate the heat input if we are heating by using that. So if we're going from 20 to 100 and we have 100 grams, all we have to do is take 100 times 80, which is the change in temperature, and then multiply that by 4.18. That would be the energy input that is required to heat that particular liquid. But that's you're not changing phases, right? So you can also cooling down, energy release. So if you're going from 80 to 60, so you can equally calculate the energy loss there by taking the mass times the change in temperature times the Fudge factor. So this is all for water, right? Now, because that value will change for different liquids. For if it's ethanol or oil, that the energy required will change, and that goes back to the intermolecular forces that have different strength between these molecules. Of course, once you reach the boiling temperature, you're not and you're boiling off water here. So this is from this point to that point. You're not changing the temperature here. You're just simply boiling until the water is all boiled off. So this is for an open container, and we already said that in order to determine the heat there, we use 44.0 kilojoules per mole, right? Since there is no change in temperature, we just need kilojoules per mole. And of course here we have a temperature, because we are increasing and decreasing temperature here. We also are using a different unit here for how much is there, grams. If I brought this into the same ballpark, it would be 7.52 kilojoules per mole. And so that will tell us, now that we have the same units, kilojoules per mole, kilojoules per mole, that tells you that there's a lot more energy required to boil, to break that hydrogen bond between water molecules than there is to just simply heat it up per mole. So kilojoules, 7.52 kilojoules per mole is, of course, much less energy than boiling. But the point here is, and this is just partial, because you also here now have you're heating steam here, for example, and we can also melt. That would be the heat of fusion. But we'll see all that later. For now, I want to talk about just the boiling point and how temperature and pressure affect that. All right. So the heat of evaporation here, or vaporization, 44 kilojoules per mole, is always constant. But the boiling point itself of different liquids varies with pressure and temperature. So those are, and so this is kind of exponential. As you can see, the pink line here is that for water. Here you see, as we expect, that at 760 torr, or millimeter mercury, if at 100 degrees, water boils. And then as you decrease that pressure, you can get the water to boil at a lower temperature. So if you cut the pressure in half, like about yay, you can see that it would boil at about 78 degrees Celsius. So it's not like if you cut the pressure in half, you're gonna boil at 50 degrees, and so it's exponential, right? So that makes our calculations more complicated, but you can actually determine the delta H of vaporization, which is constant, by using this equation here, right? So the delta H of vaporization, which of course is always constant, you can collect the pressure and temperature at different times, and then use this equation where beta is just a constant, E is Euler's constant, R is the ideal gas constant, and of course T is temperature, and P is pressure of the vapor. You also see here different substances, right? Like ethanol and diethyl ether at different boiling points. So they have much lower intermolecular forces, so they have lower boiling points at the same pressure. And then down here you have ethylene glycol, which is has a boiling point of about 200 degrees. So you can kind of see how this would eventually hit that at normal 1 atm, or 760 millimeter mercury, it would boil. So let's use this equation here and see if we can't use it to calculate or determine the vapor pressure. And so this is called the Clausius-Clapeyron equation. And so what we've simply done here, we've made it linear, this equation, to simplify it by taking the natural log of both sides. And so now if you plot the natural log of P versus the natural log of 1 over T, sorry, not natural, okay. If you plot the natural log of P versus 1 over T in Kelvin, so you have to convert that to Kelvin, and then if you take the slope will be equal to, and it's written here, it just doesn't look that great, so the slope will be equal to the negative delta H over R. So that then we can just simply take the slope times the ideal gas constant to determine the delta H of vaporization for a particular liquid. And so we can do that with in Excel, and so I'm going to show you how to plug in order to get the slope. If I'm giving you data here, like determine the delta H of vaporization by plotting P versus 1 over T, and I give you this data. Now I'm going to go into the Excel now, and I've already input the data that I've given you here. And you should, and this is important because we will be doing that in the lab sometime soon, and you will have to plot that and determine the linear equation for this data. All right. So Excel is for free. You can also borrow a computer to any of you, and so I've put that in here, and now I've put the units above. Of course, we don't want to plot this, right? And that's because I'll show you what that looks like. It's going to be exponential, and we can't really get the slope. So if I go to chart, and then I want to just have spots. I want to have scattered here, right? So we're going to plot this and go OK. You see how that's not what we're looking for, right? But you can actually right click on any of these points and then go add trend line. And so yeah, see, that doesn't look very good, but it's going to be exponential, so that's more like it. All right, but what you want to do is you want to plot 1 over t. So all you have to do is you use Excel, you write equals 1 divided by, and then you just highlight that cell and you hit enter, and then you highlight the box, and you see that little plus sign that pops in. You double click that and it will do that same function to each of the other cells. Now we can do that here as well. We want to do the natural log of p. Let me see. This is 1 over t, and this is of course the natural log of p. I apologize. And the natural log of p can also be calculated. What you want to do is equal, and you have to capitalize ln, and then in parentheses you can put that and enter, and then that will do that. And you can also highlight that and do the same thing we just did. You go to insert and then click our charts, and you want more because we want the we just simply want the scatter, and click OK. This is more like it. You can then go trend line, and the trend line one needs to be linear. And so in addition, we also want to display the equation. So you click that button on, and so now we have the equation that we can use. Alright, so we now know what the slope is, and so we can just say the delta H of vaporization, we can solve that equation. But so this is just something that we will have to do in the lab. So we plotted that data, and we now have an equation for that. So this is kind of what the spreadsheet looked like that I just showed you how to do. So we have y equals negative 3,733.5 blah blah blah, but we only need that slope, right? Because we can set that equal, we can solve for delta H. And well, I apologize for having all that worked out already, but you just, you multiply by r. We know the slope, so you plug in the slope, and the ideal gas constant is 8.314, and I will provide you with the equation, the Clausian-Clapeyron equation, as well as all of the constants. You just need to pay attention to the units and which constant to use. It has to be in joules per mole per K, and so that of course K changes, and that our answer is in joules or per mole. So here we, by using that equation, end up with a heat of vaporization of 31.4 kilojoules per mole, and I believe that was for ether. Alright, so when we come back, I'll show you a different way to determine that with the 2-point equation.